Turn that music down, please. I had to wait for the end of the track. Oh, nice. Okay. Welcome back. I mean, I could talk over the music, I guess. I could hum a little bit, but yeah. No, we still have the music. Turn the music down, please. There we go. Welcome back from lunch. Thank you for settling in. Please make sure that your phones are set to silent and your beepers are off if you still have beepers. A couple items from earlier this morning. Once again, we do apologize for the power outage that took some of the tables out and some of the APs and affected the Wi-Fi. So we had I think we had a switch or so that didn't come back after the power got restored. I did hear that everything is back up and running, so hopefully internet performance should be back to where you expect it to be. Also, the temperature, we did hear quite a bit of feedback that it was a little bit chilly this morning, and I want to say that was intentional to wake you up, but you know, that's how it goes sometimes. They did make a slight adjustment, so hopefully the second half of the day will be a bit more comfortable for everybody. So with that said, I wanted to introduce Chris, who's going to talk to us about a really neat experience, migrating routing protocols in a live data center. Take it away, Chris.
Nice. Hi everybody, I'm Chris Woodfield. I'm with the Twitter network engineering team, and I'm here to talk about a project that hopefully none of you should have to do. This was a very intensive project for us, and you know, a lot of factors came into the fact of having to do this the way we did. I see the value in sharing of it because in perfect world you wouldn't be doing this sort of project in this sort of way, but none of us live in perfect worlds. So I think it's valuable to explain how the sausages get made sometime when you don't have a perfect world where you can just do things more cleanly. So starting with our existing design. When we first started building data centers about 4 or 5 years ago, OSPF was more or less a no-brainer as far as a data center routing protocol. BGP data center topologies really weren't widely known about. The RFC didn't get published until I believe 2012. Or maybe a year after that. The feature sets of the various data center network devices, particularly lower end switches, didn't have all the complete features that were necessary to do a successful BGP data center routing deployment. Speaking to our environment, we had a rather heavy north-south bias to our traffic, and this comes back to the point that at the time, the Twitter app was a big old ball of Ruby on Rails, and there wasn't a whole lot of disaggregation of various components of the app going on at the time. So we built an OSPF topology, a standard multi-area. We had a number of clusters where we separated the clusters by role. So we had a cluster for front-end hosts, a cluster for storage, a cluster for real-time storage. And at the time, we were scaling more vertically than horizontally. In order to keep the OSPF topology as simple as we could, our preference for capacity augmentation was to expand the size of LACP trunks as opposed to adding more layer 3 links, which would make that topology more complex and introduce more SPF fun. As it happens, time goes on, and your original assumptions turn out to be completely incorrect. We saw the app deaggregate into a number of microservices that resulted in a east-west traffic explosion. We were seeing far more traffic between hosts in our data center than the traffic we were passing out to the internet. In the process of augmenting all of these links, we wound up running into capacity issues with the number of hosts, number of individual ports we could put in LACP trunks. This forced us to add more layer 3 links, which in turn made our OSPF topology more complex, and you can see how that can go. At the time we started to decommission OSPF, we had over 50,000 LSAs in our table. I don't recommend that. One particular flaw in our design that was becoming a big problem was that during certain migrations that we were doing, we were seeing traffic actually prefer paths going through other racks as opposed to up through the fabric. Never a good day when that happens. So the decision was made a number of years later. We started this project late last year. BGP data center routing had by that time had become a bit more established, and feature sets were more stable and complete. So we decided to take the plunge and to move to a BGP topology for our data center. A lot of the reasons that other speakers have described far better than I have. Policy control at every peer. It restores something of a flat routing model as opposed to a multi-area topology. Easier to diagnose, simpler decision points, and just generally more scalable. Most data centers that do these sorts of projects, based on the collective knowledge that we pulled together at the time, are going to build a new one. They're going to build a new topology, and they're going to move hosts or applications into it. If anybody has done this separately, they weren't talking about it, and I'd love to talk to you afterwards. We, at the time, were not looking at any new data centers builds. We couldn't foresee a way that we could build a new topology in our data center and migrate traffic over incrementally. Thus, we made the decision that we were going to do it live. We were going to turn up BGP inside our data center on the same topology that our OSPF was currently running on, and then tear down OSPF. So a quick description of the data center topology: a standard clause model, backbone edge routers that connect data center to backbone, as well as terminate our load balancers, firewalls. Dozens of fabric and cluster switches. I believe that we were 4 wide on fabric at the time that we started this. We've expanded that fabric and gone wider since. Thousands of top of racks. And multiples of terabits per second of traffic going between hosts in the data center. And as you might expect, Twitter is a very sensitive real-time application. There were no reasonable expectations or assumptions that we would be able to tolerate downtime during this migration. So I'm going to change tenses a little bit and talk a little bit about what we did, but also talk about, if you were looking at this sort of migration, what you might run into. The first thing that we needed to do, and that everybody doing this should do, is realize that when you're talking about data center hardware, BGP feature sets are going to be all over the map. Core backbone routers, you tend to have assumptions as to a complete feature set. With some of the lower end gear, particularly top of racks, which are the weakest links, you could wind up with a number of compromises. Fib limits, the number of routes you can install in a fib. How many ECMP next hops can you associate with a particular route? Support for specific BGP features, such as 32-bit AS numbers, multi-AS multipath. A number of devices will not ECMP across different AS paths, which was a fun one we had to figure out a solution for on the fly at one point. And in a lot of ways, the state of the existing hardware will in fact dictate your topology and your design. There are a number of variations on the clause model. There are single spine and multiple spines model. We identified an issue with going with a multiple spine model, which honestly would have been our preference, where unless we were passing down a full table to our top of racks, which we couldn't do due to fib limits, we saw black hole potential if we went to multiple spines. So a single spine it was. That spine will scale very nicely, and it should do everything we need it to do, I hope. How many spines can you put in your data center? How wide can you go? How wide can your cluster switches do ECMP? Are they 64, 128, Sometimes they might be as small as 8 or 16, depending on your hardware. That's going to limit your scalability at that point. When you assign ASNs to your network devices, do you use a shared space, or do you assign every device a unique AS number? Well, it depends. Does all your hardware support 32-bit ASNs? If so, great, do unique. Otherwise, you're going to have to make some compromises. As far as AS allocations, again, if you can use 32-bit ASNs, do it. We came up with a couple numbering schemes based on how various layers, based on the naming conventions we were using at various layers. In our case, our fabrics and clusters were based on a cluster unit number, so we used a scheme to just do some math, taking those numbers to generate AS number. Our racks, we use letter designations: AAA, AAB, AAC, so on. So developing a AS allocation scheme from that wind up being developed through some ASCII math, some pseudocodes there, using 1 to 26 for each letter in the alphabet. Aggregation is going to be an interesting one because the assumptions that you can make between OSPF and BGP are going to be different as far as how where you can aggregate networks, particularly if you're going into a clause model. In our previous cluster, there were crosslinks between cluster devices which are not going to be present in a clause model because you have to be able to scale wider. This created some black hole potential that we observed if we were aggregating and then suppressing the more specifics. You do want to float your aggregates, but you don't necessarily want to make the aggregate the only route. The rack routes themselves, when possible, should stay in your network. A few other tips that we learned along the way. From your edge, generally you only need to generate a default route. There may be some needs for some more specific routes to be floated in, but think about those carefully and make sure that they're really needed. The implication from that comes up is that if you can't send full tables down to your top of racks, that default route that's generated from the edge becomes the same default route that your racks are going to be using to talk to each other. So you definitely want your data center aggregates along with your default route to go down to the racks, because if that default route goes away, not only can your racks not talk to the rest of the internet, but they can't talk to each other either. Put those aggregates or more specifics in place and that issue goes away. If you're going to be doing any policy that manipulates local pref, remember that in an eBGP model, where each layer speaks over eBGP versus IBGP, local pref is not transitive. And the easiest way to ensure that you have consistent behavior along a path is to make sure that all your policies are the same. Something we discovered in our lab testing is that if you're running OSPF and BGP in parallel, it's necessary to turn on advertise inactive. Otherwise, your BGP routes will not propagate until they're preferred over the OSPF routes. We ran into one interesting bug. I'll tell you about the bar later as a part of this. The GShut community. The GShut is a relatively new, well-known community. Its support in various switch code is inconsistent. Some vendors have it out of the box. Other vendors, you have to implement a policy. There's an internet draft that describes its behavior, which is fairly basic. If route has community X, set local pref to 0. Don't use the route. The internet draft mentions an instruction to strip the community after receive it, but we had trouble understanding why you would want to do that, and we chose not to. Automation. You're going to be building a lot of peering statements. There is no reasonable way to do this without building and deploying your configs using software. Just no way. Not unless your network is very, very small, which ours, of course, was not. We developed 4 main phases for our automation solution for doing this rollout. First step is to discover your existing state. Again, this is a live network. This is an organic network that's grown over time. You're not going to be able to arbitrarily fit it into a source of truth. You have to go discover what's out there and pull that in. And lots of data you need to pull in. Platforms, code revs, what configs to deploy, which device roles, router IDs, and neighbor information. And this is important because if your config generation is manually building BGP peering statements, you have to know, and OSPF alone will not tell you what all the neighbors are. So there's a couple strategies around this. You could use LLDP data that each device will give you, which is great as long as you have LLDP working reliably on every device in your network. Hint, we didn't. The more reliable approach we found is to store the /31s on all the interface addresses and just find matches. Device X has 0.31, device Y has .1.31. Guess what? They're directly connected. During a project like this, you're often not going to be working on a static topology. Racks are always going to get rolled on the floor. There's always going to be changes. So this discovery should be something that you're always running continuously so that you can pick up changes as they go. The next step is to take all this data and generate your configurations. You're going to have various templates for your different vendors, your different role types. Make it a template that is easily inheritable. I realize it's the final bullet point, but Jinja 2 actually makes this very easily with includes. You can start with a baseline policy that implements everything that should live on every device, even policy that doesn't get used. It's easier just to deploy it. And just have that there, even if it's not referenced, as opposed to putting a whole bunch of conditional statements as far as what goes where. Separate your baseline from your configuration templates. That makes things much easier and allows you to do this in something of a 2-pass. You can just deploy your baseline in one big push, and then do the peer-specific config afterwards. Generally, not a whole lot of need to filter routes. Mainly we had to filter routes upstream to avoid scenic routing. Again, we don't want rack A to rack B to use rack C. And build templates for rollback too. Don't forget that. Now that we have that code in place and working, the push scripting that we developed actually was a bit of a slow roll. Again, thousands of devices, but we ran only a couple instances in parallel. We were only pushing a few racks at a time, just to manage the risk of this. We were pushing our configs in batches of 100 devices at a time. You obviously don't want to be watching this thing run. You don't want to be sitting there watching a screen. So have your code post status to a HipChat channel or a syslog. Actively alert you on errors and when the batch completes so that someone knows to start off the next batch. And then afterwards, you're going to ideally have parallel OSPF and BGP tables. They will never be completely parallel. So you have to find the differences and make sure you understand them. Make sure that every place that you had an OSPF neighbor, you now have a BGP peer. Biggest problem we ran into, blocking TCP port 179 on loopback ACLs. Check the routing tables and make sure that for every route that is still only in one protocol or the other, you understand why. Check a route, if you have a route that's only OSPF, check the covering BGP route and make sure the next hops match. That was a very valuable audit to do. Now it's time to turn OSPF off. So how did we do this? There's 2 main ways that you could do a protocol decommission. Do you just turn off the neighbors, or do you adjust the routing preference to make your new routing protocol the more preferred routing protocol? We actually did a little bit of both. At the cluster to rack layer, we made the decision to disable the OSPF neighbors and trust that the BGP routes, obviously after validating, would take over as the preferred routes. The reason for this is that we decided that it would be far easier to deactivate those peers at the cluster switch in batches. That way we could roll those back easier without having to touch all of those racks in parallel. One place to turn off, one place to re-enable if needed. From the cluster to fabric to edge layer, we actually did this part with preference changes, turning up the preference for BGP. For OSPF to make BGP the more preferred route. Once we had this accomplished, with all the OSPF routes still on the table, auditing the remaining OSPF routes was far easier. One lesson we learned is it's perfectly fine to run these two protocols in parallel for extended periods of time. So don't feel like you have to rush this step if you don't have to. And as a result, we actually had a pretty good experience with this rollout. We only caused one incident during this entire project, and the reason for that is that we had multiple data centers that we could fail the app in and out of, and there's always going to be a little bit of packet loss as we do these cutovers that we were mitigating the risk by failing different parts of the app in and out based on what cluster we were working in. One point where we had bad information resulted in one facing incident because we thought we were working on a low SLA rack and we were not. One app, an interesting anecdote that came out of this is that we had one app we were very worried about just because of the sensitivity of the app and the amount of traffic involved. The solution that we came up with after talking to those service owners was turn off all their racks at the same time. Turn off OSPF on all of their racks at the same time. The end result, a bit of a subtle but important change in statement. And the result of that is that app had 1 minute of impact. They dropped below SLA for 1 minute, bounced right back. Everything was cool. And that drives home definitely the need to make sure that when we're doing a change like this, you got to communicate with everybody else that you're working with. We have a control center, we have various app owners, and just communication is key in large projects like this, which is interesting because you're dealing with a lot of developers that may not really know about the network, but you have to make them understand the implications of what you're doing. One nice graph that came out of this is this is RPD on one of our cluster switches before and after turning off OSPF. We weren't expecting that dramatic a difference, but we were very happy to see it. That said, not everything goes perfectly. So I'll take a few minutes and talk about the things that we did wrong or the things that we didn't expect. A lot of these are general lessons, some more specific to our implementation. But the first rule to remember in a large project is that lab is not production. There will always be subtleties. You will always run into corner cases that you just could never have simulated in your lab due to scale or whatever other reasons. Canarying early and often is a strong recommendation. That's how you're going to catch things that you didn't catch in your lab. Automation. Our automation was good but not great. This project had a lot of time pressure around it, and our developers did an incredible job. But at some point, we just had to say, all right, it works good enough. Are there things we wish the automation did that we didn't develop? Sure, but what we had was enough to get the job done. This is also a project that we've only done, it was one project, not an ongoing initiative. If it had been, we might have spent more time there. We moved very fast, and as a result, the documentation and runbooks fell behind. Document first, deploy later. Again, the one impacting incident that I mentioned, because we didn't have perfect information on what was running in a particular set of racks we were working on. Going back to the G-Shut implementation, that actually was something that we missed the first time around. We actually failed to deploy it, and we deployed it in one platform but missed the policy to deploy it in another platform, so we had to retro. Later on down the line, and by the line I mean 2 months after we completed the project, we ran into this problem, which was that in a clause model, you're going to have routes coming up from your racks that are going to have shorter paths, but you're also going to be bouncing prefixes if you don't filter them through other spines. So we saw a situation where if a fabric lost connectivity to a particular cluster, now granted, no traffic would hit that spine because it doesn't have a route there, but in that spine device's routing table, its best route to host in that cluster was an ECMP path through every other cluster in the switch via all the various spines. This resulted in a minor incident just due to the fib scale going a lot wider than we ever expected. That required us to add some additional filtering to make sure that no cluster would advertise up a route that was not local to that cluster. So that's been resolved. All in all, things are working well for us. We're still iterating, we're still improving, hopefully this is the tail end, and we're not going to have to do this again. It was a pretty intense project, to say the least, but I think we made a lot of progress, and I'm very happy with our work in the end. Thank you. Questions?
Hi, Kevin Bloomberg. Quick question for you.
Yes.
Did you compute after this how many additional hours of sleep you got due to the conversion?
I really should have. There were a lot of late nights here.
No, but what I actually meant was how much extra sleep you got because you weren't running with 50,000 LSAs and issues related to that.
I can tell you that network incidents in the quarter after we completed this deployment were down by half.
Thank you.
Good morning, Chris. Matt Petak, Yahoo. I noticed you didn't actually tell us whether you decided on the 32-bit ASN, 16-bit ASN, and the like. I guess that's left as an exercise for the reader.
We got lucky, and we didn't have anything in our network that didn't support 32-bit, but I know there's people who have not had the same experience.
And one other question, you said 50,000 LSAs before you started. I'm curious, did you actually track how many prefixes were in your BGP after you were done?
Yes, far fewer than 50,000. Around mid to high thousands, and we're working on that. We're doing more we're doing more aggregation to a lot of those are /31 link nets that were aggregated in OSPF, but the way that we did our link numbering, we couldn't aggregate in BGP as well. But we're doing a renumbering project now so that we can bring those back into aggregates and reduce that fib further.
You shouldn't have any scaling problems with that low a number, though, so it should be safe. All right, thank you.
Hi, I'm Sue Harris.
Hi.
I'm also a BGP chair in ITF. So, question is, did you have interoperable G-Shut community implementations? I wasn't quite clear on your problems that you were listing there. And as a chair, should we push standardization of that faster?
Okay, so there's a draft on the G-Shut community. I don't think I've ever actually gotten an RFC number. Some of our switch OS vendors support G-Shut natively. If there's no additional config needed, if I see the community, I'm setting localpref 0. Other vendors, we built policy to replicate the behavior. just with match set policies. There's a bit in the draft where the recommendation is to, if you receive a route with a GSHUT community set, to set your local ref to 0, but then also strip the community from the prefix. So if you pass that prefix along, you're sending it without that GSHUT community. We couldn't figure out why that would be something we would want to do. In our opinion, if you have a route that's poisoned, it should stay poisoned all the way through. And actually, when we talked to one of our vendors, the vendor that I mentioned did support it natively, they came to the same conclusion.
Okay, thank you. That's really good feedback.
Hi, Rüdiger Volk, Deutsche Telekom.
Just one moment, want to make sure we have 2 more questions, and we're closing the mics after this.
Just a follow-up on the GSHUT. As you had the choice in some cases to do the GSHUT policy yourself or rely on the vendor's implementation, which way did you feel more comfortable about?
If I would say that, just from having more control over my environment, I would say I have a weak preference for being able to define the policy myself. Now, the one vendor that supports it natively, they do provide touch points so that you can modify the policy, but we wound up using their default policy in that OS.
Owen DeLong, Akamai. You're going through a renumbering project to aggregate your link addresses. Why bother to carry them at all?
There are some reasons for that, and we did consider that, but we found that there are some other reasons. I'll tell you out of the bar. That's the best I can explain it. We actually found that there were some things that broke pretty badly. Monitoring being the first thing. Monitoring was pinging those link nets. I don't necessarily need to do that, and that's something we're discussing, whether or not that's a necessity. DHCP forwarding on our network, on our top of racks, actually sources the unicast's DHCP request using link net address, not a loopback. That's what broke the worst. And I saw you put your head to your hand. We had the same reaction.
Alrighty, thank you so much, Chris. Really appreciate that.